For most of human history, the stars have represented possibility. They were never walls or limits. They were distant lights that suggested a future larger than Earth, a reminder that humanity was part of something vast and unfinished. Long before rockets or telescopes, people assumed that reaching other stars was a matter of time, not permission. But here is the shocking possibility. What if interstellar travel is not only possible, but unavoidable? Not because it is easy or safe or within our immediate reach, but because the laws of the universe quietly allow it. This idea challenges a growing belief that space is simply too extreme to cross, too empty, too violent, too hostile for living beings to survive for decades while moving at unimaginable speeds. According to this view, every civilization may eventually hit the same invisible wall, trapped forever around its home star. Yet when we examine the universe closely, something unexpected emerges. Physics does not forbid travel between the stars. There is no fundamental law that says a spacecraft cannot approach a fraction of the speed of light. No rule that says matter must disintegrate if it tries. What physics does say is that the journey will be expensive, dangerous, and unforgiving. Survival is not guaranteed. Comfort is irrelevant. But possibility remains. This distinction matters. The universe is not young. It is billions of years old, filled with stars that formed long before our sun. If intelligent life arises even rarely, then some civilizations may have had enormous amounts of time to experiment, fail, adapt, and try again. If interstellar travel were truly impossible, the universe would enforce that limit absolutely. But instead, it merely raises the cost. That suggests a different interpretation of the great cosmic silence. Perhaps the absence of obvious alien activity is not evidence that no one can travel between stars, but evidence that doing so is extraordinarily hard. Perhaps the universe is not empty, but patient, waiting for civilizations willing to accept risk on a scale never before attempted. This reframes humanity's situation entirely. We may not be trapped. We may simply be standing at the very beginning of a path that almost no one has yet managed to walk. So the question is no longer whether interstellar travel is dangerous. That much is obvious. The real question is whether danger has ever stopped a species that learned how to understand it. Every major leap in human history began the same way, with fear, uncertainty, and the knowledge that failure was possible. Crossing oceans, reaching the poles, leaving Earth itself. None of these were safe. All of them reshaped our future. Interstellar travel may be the most extreme version of that pattern yet. And whether or not we succeed, the fact that the universe allows the attempt may be the most mind-bending discovery of all. If interstellar travel is possible in principle, then the first obstacle is not danger, radiation, or engineering. It is distance. The space between stars is not just large, it is violently large in a way that the human mind struggles to hold. Our nearest neighbouring star system lies more than 4 light-years away, a span so vast that even light, the fastest thing in the universe, takes years to cross it. Compared to this, every journey humanity has ever made on Earth is negligible. At the speeds our current spacecraft can achieve, reaching another star would take tens of thousands of years. Entire civilizations could rise and fall while a single ship drifts through the dark. For interstellar travel to matter to living beings, the journey must be shortened to something closer to a lifetime. That requirement forces us into a strange and unfamiliar regime of physics, where speed itself becomes the central problem. To cross interstellar distances in decades rather than millennia, a spacecraft must travel at a significant fraction of the speed of light. This sounds impossible at first. Light speed feels like a hard boundary, a cosmic speed limit designed to keep stars isolated from one another. But once again, physics surprises us. While nothing can reach the speed of light, approaching it is not forbidden. Doing so, however, demands enormous energy. Accelerating even a modest mass to relativistic speeds requires power on a scale far beyond anything humanity currently produces. Every additional kilogram becomes a liability. Every system, every structure, every safety margin adds to the cost. Interstellar travel is not constrained by imagination, but by efficiency. This is why most realistic concepts for early interstellar missions look nothing like traditional spacecraft. They are stripped down, optimized, and unforgiving. Some designs rely on vast laser arrays pushing ultra-thin sails from afar. Others imagine engines powered by nuclear fusion or more exotic reactions. None of these ideas violate known physics, but all of them exist at the very edge of what a technological civilization might realistically build. And even if the energy problem is solved, another challenge remains. Acceleration is only half the journey. A ship that reaches relativistic speed must also slow down. Without deceleration, it becomes a projectile, unable to stop, unable to explore, unable to survive arrival. This doubles the difficulty and forces engineers to confront trade-offs with no perfect solutions. Distance, then, is not a single problem, but a chain of them. Energy, mass, time, and precision all compound until the journey feels almost unreasonable. Almost. Yet distance alone does not make interstellar travel impossible. It merely ensures that only civilizations willing to invest staggering resources, patience, and risk will ever attempt it. The universe does not close the door. It simply makes sure that stepping through it is never trivial. And once a ship finally reaches those speeds, once it commits to crossing the gulf between stars, distance stops being the greatest threat. Because then, space itself begins to fight back. Once a spacecraft reaches interstellar speeds, distance is no longer the primary concern. The real danger is what fills the space between the stars. Interstellar space appears empty, but this is an illusion born of scale. It is permeated by gas, dust, and high-energy particles, known collectively as the interstellar medium. Under ordinary circumstances, this material is harmless. But at relativistic speeds, even the smallest particle carries destructive power. A single atom, encountered at a significant fraction of the speed of light, strikes with the energy of a microscopic bullet. Multiply that by trillions of impacts over years of travel, and the vacuum becomes something closer to a storm. Space does not need to be crowded to be lethal. It only needs speed. The most alarming threat comes from dust grains. In planetary systems, grains large enough to cause catastrophic damage are relatively common. At interstellar speeds, a collision with one would release energy comparable to an explosive, enough to destroy a spacecraft instantly. For this reason, an interstellar journey cannot begin by moving sideways through a solar system. The ship must first escape upward and outward, leaving behind the dense debris of its birthplace. Beyond the planetary plane, conditions improve. Large dust grains become vanishingly rare, and the remaining material shifts from catastrophic threats to cumulative damage. Impacts no longer shatter the ship, but they erode it. Over years of travel, the forward surface is slowly ablated, atom by atom, grain by grain, as energy is dumped into the hull. This damage is severe, but not fatal. Calculations show that even after crossing several light years at high speed, the erosion amounts to millimeters, not meters. The solution is conceptually simple: shielding. A sacrificial forward layer absorbs the damage, protecting the rest of the ship. Shape becomes strategy. Long, narrow designs reduce exposed area, turning survival into an engineering problem rather than a physical impossibility. Yet impacts are only part of the story. Gas atoms striking the hull do not merely heat it. At extreme velocities, they penetrate deeply, strip electrons, and transform into high-energy radiation inside the ship. This radiation is invisible, relentless, and deadly. Without protection, a crew would be exposed to doses comparable to those inside a nuclear reactor. To survive, the ship must carry mass not for propulsion, but for defense. Dense materials and thick layers of water slow incoming particles, converting lethal radiation into manageable heat. The shielding does not need to be perfect, it needs to be sufficient. This marks a turning point in the story of interstellar travel. The universe is not actively trying to destroy travelers, but it demands preparation. Space punishes carelessness, not ambition. The conclusion is unsettling and hopeful at the same time. The interstellar medium does not make travel impossible. It merely ensures that only ships designed with precision, restraint, and respect for physics will endure. And even then, another danger remains. one that arrives from every direction, cannot be outrun easily, and ignores the ship's forward shields entirely. Cosmic radiation. The greatest threats of interstellar space are not the ones you can see. After shielding against dust and gas erosion, a spacecraft may appear intact, its hull scarred but functional, its systems operating as designed. From the outside, the journey looks like a success. Inside, however, a far more dangerous process may be unfolding. Radiation is the silent consequence of speed. At relativistic velocities, the atoms of interstellar gas do more than collide with the hull. Many penetrate it. Hydrogen atoms, the most common particles in the universe, pass deep into the ship's structure, where they are stripped of electrons and transformed into high-energy protons. In effect, the ship manufactures radiation as it moves. For an unprotected crew, the result is catastrophic. The radiation levels inside such a vessel would rival those found at the core of a nuclear reactor. Exposure would be lethal in minutes, long before the ship ever reached another star. No explosion, no warning, just biology quietly overwhelmed by physics. Survival demands mass. Dense materials slow and scatter incoming particles, converting dangerous radiation into heat that can be managed. Metals such as titanium provide effective barriers, but one of the most efficient shields is also one of the most ordinary substances imaginable. Water. A thick layer of water surrounding crew compartments absorbs radiation while serving a second purpose as life support. Nothing carried aboard is allowed to be single-use. Even this solution has limits. As speed increases, so does radiation. At higher fractions of the speed of light, shielding requirements grow rapidly, turning meters of protection into tens of meters. Every added layer increases mass, and every added kilogram demands more energy to accelerate and decelerate. Interstellar travel becomes a careful negotiation between survival and feasibility. And still, radiation finds a way in. Cosmic rays arrive from outside the ship's path, accelerated by distant supernovae, black holes, and the magnetic fields of the galaxy itself. Unlike interstellar gas, they do not care which direction the ship is facing. They strike from all sides, passing through hulls and shields with relentless persistence. Perfect protection is possible in theory, but punishing in practice. Enclosing an entire spacecraft in thick radiation shielding would make it too massive to reach interstellar speeds with early propulsion technologies. For the first travelers, absolute safety may be unattainable. This forces an uncomfortable conclusion. Early interstellar missions will likely involve risk not just to machinery, but to life itself. Increased cancer rates, genetic damage, and long-term health effects may be the price of reaching another star. The universe does not forbid the journey. It simply demands that those who attempt it accept consequences measured not in broken hardware, but in years of life. And yet, even radiation does not close the door. It narrows it. The final question is no longer whether a ship can survive the journey, but whether a species is willing to endure what survival costs. By the time a spacecraft is capable of surviving distance, erosion, and radiation, one truth becomes unavoidable. Interstellar travel is not a technical challenge alone, it is a human one. The earliest missions between stars will not look like heroic expeditions from fiction. They will be exercises in restraint. Crews will be small, ships will be narrow and enclosed. Every system will serve multiple purposes, and every gram of mass will be argued over. Comfort will be sacrificed long before safety, and safety will still be incomplete. Time itself becomes a cost. Even at a significant fraction of the speed of light, journeys to nearby stars take decades. These missions are not round trips. The people who leave Earth will do so knowing they are unlikely to return. They will age in transit, live entire portions of their lives inside sealed environments, and arrive at destinations that may still be unknown in critical ways. This changes the nature of exploration. Interstellar crews are not explorers in the traditional sense. They are settlers, scientists and test subjects at once. Their mission is not only to reach another star, but to prove that living systems can endure the journey at all. Every voyage carries biological uncertainty alongside mechanical risk. The cost extends beyond individuals. Building an interstellar-capable civilization demands enormous resources, energy production on unprecedented scales, long-term political and social stability, a willingness to invest in projects whose payoff may not arrive for generations. Any society attempting this must value continuity over immediacy and cooperation over speed. And yet, this price is not without precedent. Human history is shaped by ventures that once seemed irrationally expensive and dangerous. Ocean crossings, polar expeditions, and the first journeys into space all faced fierce opposition grounded in practicality. Each required societies to accept loss, failure, and long periods without success. Each eventually reshaped the trajectory of civilization. Interstellar travel magnifies this pattern rather than breaking it. The risks are higher, the timelines longer, and the consequences more permanent. But the underlying logic remains the same. Expansion has never been safe. Survival has never been guaranteed. What changes now is scale. The decision to leave one star for another is not simply an act of exploration. It is a declaration that a species intends to persist beyond the lifespan of any single world. It is an acknowledgement that planets fail, stars change, and long-term survival may require movement. Seen this way, the dangers of interstellar travel are not arguments against it. They are the cost of choosing endurance over comfort. The universe does not reward this choice quickly. It does not promise success. But it does allow the attempt, and that may be enough. Because once a species accepts the price of the journey, the question shifts again. Not whether interstellar travel is possible, but whether staying home is the greater risk. Once the cost of interstellar travel is fully understood, the great cosmic silence begins to look different. For decades, the absence of alien civilizations was treated as a paradox. In a universe so large and so old, intelligent life should have appeared many times. Some of those civilizations should have become advanced, and at least a few of them should have spread outward, leaving unmistakable signs of their existence. Yet when we look into space, we see no clear evidence of anyone else. But this reasoning quietly assumes that interstellar travel is easy once a civilization becomes advanced enough. That assumption does not survive contact with reality. As we have seen, crossing the space between stars demands extreme energy, long-term stability, and a willingness to accept risk over decades or centuries. It requires civilizations to solve problems not just of engineering, but of biology, sociology, and patience. Many societies may never reach that point. Others may reach it briefly and then collapse before acting. From this perspective, the silence of the universe is no longer mysterious. It may simply reflect how rare it is for a civilization to align all the necessary conditions at the same time. Technology must advance far enough. Resources must remain available. Social structures must remain stable. And the motivation to leave must outweigh the instinct to remain safe. Even if interstellar travel is possible, it may not be common. This reframes humanity's position in the universe. We are not necessarily alone, and we are not necessarily special, but we may be early in developing the technologies required to attempt interstellar travel, and early in confronting the long-term choices that determine whether a civilization spreads outward or remains bound to its birthplace. The absence of evidence, then, is not evidence of impossibility, it is evidence of difficulty. This idea carries an unsettling implication. If the universe is quiet because interstellar travel is rare but achievable, then the future is not predetermined. Civilizations do not automatically become starfaring. They choose whether to try, and many may decide the cost is too high. Humanity now approaches that same decision point. The challenges ahead are real, the dangers are unavoidable, but the path forward exists. Physics allows it, nature tolerates it. The silence of the stars may not be a warning, it may be an invitation. Because if interstellar travel is possible but uncommon, then the first civilization to commit to it does not merely explore the galaxy, it changes the story of life in the universe. And that raises the final question. If the universe allows the journey and the cost is known, what will we choose to do with the time we have? If interstellar travel is rare because it is difficult, then a deeper truth emerges. The greatest danger to a civilization may not be the journey outward, but the decision to remain where it began. Every species that evolves on a single planet inherits the same vulnerability. Worlds change, climates shift, asteroids strike, stars age and grow unstable. Even without sudden catastrophe, no planet remains habitable forever. Geological and stellar timescales guarantee that home is temporary. For most of human history, this fact did not matter. Survival was measured in generations, not epochs. But a technological civilization inevitably begins to think further ahead. Once a species understands that extinction is not hypothetical but inevitable, without adaptation, long-term survival becomes a strategic problem. From this perspective, interstellar travel is no longer an act of curiosity. It becomes a form of insurance. Remaining bound to a single star concentrates all risk in one place. A civilization may thrive for thousands or even millions of years, yet still be erased by a rare event it cannot control. Spreading to other systems does not eliminate danger, but it distributes it. Failure in one location does not mean failure everywhere. This logic explains why the immense cost described earlier may eventually be accepted. Not because the journey is appealing, but because the alternative is fragility. Stability without expansion is an illusion, maintained only for as long as nothing goes wrong. The decision to attempt interstellar travel, then, marks a transition. A species stops thinking of itself as planetary and begins thinking of itself as persistent. Survival is no longer tied to a single world, a single orbit, or a single star. This shift does not happen quickly. It may take centuries of debate, failed experiments, and incremental progress. Early missions may be limited, slow, and imperfect. But once the first successful crossings occur, the logic compounds. Knowledge spreads. Technology improves. The path becomes clearer with each attempt. At that point, expansion does not require constant heroism. It becomes routine, gradual, and deliberate. The galaxy is not conquered, it is patiently occupied. Seen this way, the universe's silence gains a final interpretation. It may not be empty, it may simply be sparse, with civilizations separated by vast distances and long times, each moving outward cautiously, each learning at its own pace. Humanity now stands before the earliest version of that choice. The physics allows movement. The risks are understood. The cost is high, but finite. The question is no longer whether interstellar travel is possible. It is whether a species that knows its home will not last forever can afford not to try. Every transformation in human history begins quietly, not with celebration, but with preparation. Interstellar travel will be no different. The first attempt to cross between stars will not be a grand migration or a dramatic leap into the unknown. It will be cautious, incremental, and deeply conservative. Before living crews ever depart, machines will go first. Probes will test propulsion systems, shielding concepts, navigation, and communication across light-year distances. Each mission will answer questions while raising new ones. When the first crewed crossing is finally attempted, it will represent the accumulation of generations of refinement. The ship will not be fast by cosmic standards, nor elegant by fictional ones. It will be built around endurance rather than speed, reliability rather than ambition. Its success will depend less on breakthrough technology than on careful integration of what is already known to work. The journey itself will not be dramatic in the way stories often imagine. There will be no sense of motion, no rushing stars, no visible destination growing larger in a window. Years will pass inside a closed environment, governed by routine, maintenance, and patience. Survival will depend on stability, both mechanical and psychological. Arrival will not mean safety. Reaching another star system does not guarantee a habitable world, friendly conditions, or immediate reward. The first crews will arrive as outsiders to unfamiliar environments, still dependent on the systems that carried them across the void. Exploration will proceed slowly, cautiously, with contingency plans layered upon contingency plans, and yet something irreversible will have occurred. The moment a living crew successfully crosses interstellar space, the question of possibility disappears forever. The journey will no longer be theoretical or aspirational. It will be historical. A boundary that existed only in expectation will have been crossed. From that point forward, the logic of expansion changes. Future missions will not debate whether the journey can be done, but how to improve it. Speed increases become worthwhile. Risk decreases incrementally. Infrastructure begins to form, sparse at first, then more reliable. This is how interstellar presence grows, not through sudden conquest, but through repetition. One mission becomes two become a handful. Over long timescales, star systems become connected, not by constant travel, but by continuity of effort. The universe does not need to be crowded for this to matter. Even a thin network of interstellar civilizations would permanently alter the story of life. The first crossing would not mark the end of humanity's isolation. It would mark the end of inevitability. From then on, extinction would no longer be guaranteed by the loss of a single world. The stars would no longer be distant lights. They would be destinations. After the first successful crossing, the universe does not suddenly feel smaller. The distances remain vast. The journeys remain long. What changes is not scale, but direction. Interstellar expansion does not explode outward. It unfolds gradually, almost invisibly across timescales that dwarf individual lives. New missions depart years or decades apart. Each one builds on lessons learned from the last. Designs improve. Failures become rarer. The process is slow, not because progress stalls, but because caution is rewarded. Star systems do not become bustling hubs overnight. Most remain quiet, visited only occasionally, their environments studied carefully before any permanent presence is attempted. Interstellar civilization, if it emerges at all, is sparse by design. Density is a liability. Redundancy is strength. Communication reinforces this pattern. Messages between stars take years to arrive. Decisions cannot rely on constant coordination. Each outpost must operate with a high degree of autonomy, capable of surviving isolation without immediate support. This shapes culture as much as technology. Interstellar societies value foresight, resilience, and continuity over speed and spectacle. Over long periods, something subtle happens. The galaxy becomes connected not by traffic, but by persistence. Knowledge spreads outward slowly, carried by travelers, archives, and signals that outlast their creators. Even if expansion stalls in one region, it continues elsewhere. Progress does not depend on momentum, only on survival. This model explains why the universe might still appear empty. A slowly expanding civilization leaves few obvious signatures. No bright beacons, no constant traffic, just small, durable presences separated by immense distances and long silences. From a distance, such a galaxy would look unchanged. But it would not be. Life would no longer be confined to single worlds. Extinction events would lose their finality. The loss of a star system would be tragic, but not decisive. The story of life would extend beyond the lifespan of planets and even stars. This is the long future implied by interstellar travel. Not dominance, not abundance, but endurance. The universe does not become crowded. It becomes resilient. And in that quiet transformation lies the true significance of the journey. Interstellar travel does not promise glory or certainty. It offers something rarer. Time. Time for life to continue, adapt, and persist in a universe that changes slowly, but never stops changing. Which brings us to the final question, not whether interstellar travel is possible, but what it ultimately allows life to become. By the time we reach this point, the question that began the journey has quietly transformed. Interstellar travel is no longer a debate about engines, shielding, or distance. It is a question about identity. The universe we inhabit is vast, indifferent, and constantly changing. Stars are born and die. Worlds form, evolve, and eventually become uninhabitable. Nothing that remains still lasts forever. Life, if it is to persist, must adapt not only biologically, but strategically. Interstellar travel represents the moment a species recognizes this truth and responds to it. not with optimism or arrogance, but with responsibility. It is an acknowledgement that survival cannot depend on a single planet, a single climate, or a single star. It is the decision to accept uncertainty in exchange for continuity. Nothing about this path is guaranteed. Ships will fail, missions will be lost, entire efforts may collapse and need to be rebuilt by future generations. Progress will not be linear, and success will not be evenly distributed. The universe does not reward ambition quickly, and it does not forgive carelessness. Yet what matters is not perfection, but persistence. A civilization that commits to interstellar travel is not chasing conquest or escape. It is choosing to extend the story of life beyond the fragile boundaries that once defined it. Each crossing, no matter how small or slow, pushes extinction further away. Each outpost, no matter how isolated, becomes a safeguard against finality. From this perspective, the silence of the stars is no longer unsettling, it becomes neutral. The universe does not promise companionship, but it does not deny opportunity. It offers space, time, and the rules by which both operate. Whether those rules are enough depends entirely on the choices made by those who understand them. Humanity now stands at the earliest edge of that decision. The physics has been tested, the risks are known, the costs are severe but finite. Nothing fundamental stands in the way except hesitation. Interstellar travel will never be easy. It will never be fast. It will never be safe in the way staying home feels safe. But staying home is only safe for a while. The ultimate question is not whether we can cross the space between stars. It is whether we are willing to think far enough ahead to try, because the universe does not demand that life spread among the stars. It simply allows it. And in a cosmos where nothing lasts forever, that permission may be the most extraordinary thing of all.